I welcome back all to the course on Control System Engineering. In this video, we are going to learn the signal flow graph representation of the given system and the transfer function derivation using Mason's gain formula. In the previous video, we have learned what is meant by signal flow graph and how to represent a signal flow graph and how to convert the block diagram representation into the signal flow graph representation, and what is the advantage of signal flow graph method, and what is the Mason's gain formula with simple examples we have learned in the previous videos. In this video, we are going to learn using the Mason's gain formula. We are going to represent the signal flow graph for the complicated systems are some examples of control systems, and we are going to derive the transfer function with examples. Now let us start with this example. In this example, the signal flow graph is directly given, and what we are going to do is we are going to derive the transfer function of this system, that is y of s by r of s ratio. We are going to find using Mason's gain formula. In the Mason's gain formula, we learned that we have to first find the number of forward paths and what are the forward path gains. Then we have to find the loops, all possible loops existed in the system, and loop gains we have to find. Then we have to find the non-touching loops, 2 non-touching loops, 3 non-touching loops, and so on. Then using all these gains, we have to uh, substitute these gains in the Mason's gain formula. Therefore, finally we will get the transfer function of the given signal flow graph. Now let us start by finding the forward paths. See the diagram and try to identify the forward paths. How many forward paths are there? Just recall what is meant by forward path. Forward path is a path starting from input and ending at output node. So from input to output, see this is the input node, and if you start from here, how to reach y of s, this is one way and this is second way. So definitely we have minimum two forward paths. Okay, let us start from here to here. Okay, then it is going this way. It can't go this way because of the arrow direction. We have to definitely go in this direction, and also we can't go this way. We have to go this way, and we have to go here. So r of s to y of s, we have this path. This is a forward path, first forward path, and its gain is g1, g2, g3, g4. Now go to the second forward path from here to here. Then it can't go this way. We have to go this way, and we have to go this way, and this way, finally reach y of s. So this is the second forward path. And what is the forward path gain? G5, G6, G7, G8. So we have two forward paths. First forward path gain and second forward path gain we have written. Then let us come to the loops. See here, this is a loop. Clearly we can understand in this diagram. One loop, and this is the second loop. This is the third loop, and this is the last loop. Okay, these are the four loops we have. So four loops. Any other possible loops? From here to here, here to here? No, this arrow mark is in opposite direction, so we can't do that. So there are no other possible loops. So we have only four individual loops. Now come to the non-touching loops. Please try to identify, then I'll show it. See here, this is a loop, first loop, and try to find the non-touching loops for this first loop. If you see the second loop is touching at this point. So second loop and first loop are not non-touching. First loop and third loop both are completely independent. So these two are non-touching loops. So first non-touching loop is this one, L1 and L3. Second non-touching loop, L1 and L4. These two are also independent. Now two non-touching loops over. Now come to second and third, will compare. Second and third also both are independent. Therefore these two are again non-touching loops. Second loop and fourth loop also both are independent, so two non-touching loops. Total, finally we have four non-touching loops: L1 L3, L1 L4, L2 L4, L2 L3. The loop gains, of course, you can write. We know L1 and L3 combinedly product. You can write it similar way for other non-touching loops also. We can write the gains. After finding all these things, what should we do? We should find delta calculation and delta 1, delta 2 calculations. Okay, three non-touching loops anyhow not there, you can leave it. Then delta calculation. Delta formula is delta is equal to 1 minus of sum of the individual loops L1, L2, L3, L4 plus sum of the non-touching loops, two non-touching loops. So L1, L3 is the first non-touching, second non-touching L1, L4, third non-touching is L2, L3, fourth non-touching is L2, L4. The sum of these non-touching loops. So three non-touching loops are not there, so remaining terms you can remove. Therefore, delta after substituting L1, L2, L3, L4, we will have delta is equal to this much. Now come to the delta 1, delta 2. Since we have two forward paths, we have to find delta 1 and delta 2. The delta 1. This is the delta 1. Delta 1 is nothing but we have to first remove the first forward path. So first forward path in the signal flow graph, we have to remove it. This is the remaining signal flow graph. In this path, any loops are present? Yes. See, even after removing the first forward path, still some loops are exist here. This is L3 and L4. Therefore, delta 1 is equal to 1 minus of these individual loops which are not touching the first forward path. So L3 plus L4. Then substitute L3 value and L4 value. We'll get like this. Then find delta 2. Delta 2 means remove the second forward path and keep the first forward path as it is. After removing the second forward path, this is the second forward path. If you remove this path, this all nodes will be removed. Therefore, of course, input and output we can't remove. Only in the middle, these paths we removed. These branches we removed. Therefore, remaining all will be there. That is this. Now, what are the loops exist in this after removing the second forward path? We have L1 and L2. This L1 and L2 are not touching the second forward path. That is the meaning. Therefore, delta 2 is equal to 1 minus of L1 plus L2. After substituting L1 and L2 values, we got like this. Now, substitute in the Merson's gain formula. So, Merson's gain formula is here P1 delta 1 plus P2 delta 2 by delta, because here we have only two forward paths. So P1 delta 1, P2 delta 2 enough. After substituting all this P1, P2, delta 1, delta 2 and delta values, we will have this transfer function. I think you understood how to find the transfer function from the given signal flow graph. Now let us see one more example. In this example, signal flow graph with all variables, intermediate variables with all gains are given. Don't bother about the intermediate variables like V4, V3, V2, V1 and all. It's not just just for signal representation it is given. Other than that, it is not required for the transfer function derivation. In this, In this, we'll see how many forward paths exist first. So here we have started from here R of S and we are going to this path. This path we can't go because of opposite direction. This also opposite direction, so we can't go. So forward path is this one only. At this point, we have only one option, this way. At this node, we have to go definitely this way only. This way is not possible. So this way we have gone. And at this node, we have only one option. Straight away, go to C of S. So we have only one option from traveling from R of S to C of S node. Therefore, concluded that only one forward path existed for this problem. Now, forward path gain is G1, G2, G3, G4, G5. That's all. Now come to the loops. This is the forward path. That's it. Then loops. Loops are, this is the first loop and this is second loop and this is the third loop and finally it's a bigger loop. Big loop. So that is L4. Therefore, finally we have found that 4 loops existed in this problem and the respective loop gains we have noted it. Now come to the non-touching loops. Just verify L1, L2 both are non-touching. Yes, this and this are completely independent. So L1, L2 are non-touching. Then L1, L3 also independent, both independent, isolated. Therefore, these two are also non-touching. Then L2, L3, these two are also non-touching. But what about L4? L4 is touching with L1 and L2 and L3. All are non-touching with L4. Therefore, that is not non-touching. So we have only 3 non-touchings. L1, L2, 1, L1, L3 second, L2, L3 third. So these are the non-touching loops and their respective gains. Now come to 3 non-touching loops. Any 3 non-touching loops exist? Every time for every problem we have to verify first 2 non-touching loops, then we have to go for 3 non-touching loops. Sometimes we can find 3 loops non-touching to one among other. Therefore, here see in this example L1, L2, L3, 3 are independent, 3 are not at all touching. So we have 3 non-touching loops. So L1, L2, L3 is a 3 non-touching loop. Of course, more than that we don't have. Therefore, only 3 non-touching loop in this example. Now we'll write the delta and delta 1. Delta, of course, only delta 1 is there. Delta is equal to 1 minus of sum of the loop gains. Sum of the loop gains written. Then plus here. Then L1, L non-touching, 2 non-touching loops first, plus 2 non-touching loops L1, L2, L2, L3 and L1, L3. So plus of 2 non-touching loops, sum of 2 non-touching loops, then minus of 3 non-touching loops, sum of 3 non-touching loops. Only 3 non-touching loop is there, so 1 loop gain only. Next, delta 1. Since we have only one forward path, we can find only one delta 1. That is, after removing this first forward path, any loop exists. After removing this also, we have one loop exists, that is L3. Therefore, 1 minus L3 loop gain. Now we substitute. See, after removing the first forward path, still we have one loop, that is L3 here. 1 minus of this loop. Now substitute in the Merson's gain formula, then we can get it, the transfer function. Now let us move to the next example. In this example, of course, it's looking very complicated example. Many loops are there, forward path, Okay, let us say, let me go quickly. Actually, it's you already came to know how to find the forward paths, loops, and non-touching loops. So a little bit faster I will go. There are three forward paths. Here, the start with this here. No need to confuse how to find the forward paths. Start from x1 and you should reach a last node, that is x8 here. That's what. Just to go start and end there. How many ways you can reach the end point is the question. That is called the number of forward paths. Try all the possible ways. Here from x1 to x2, then x2 to this x3, then x4. Of course, straightly you can go one path. Second path is from x1 to x2. From x2 you can divert like this, jump to x4 directly, then straight away you can go. That is second path. Third path is from this you can go this way also, directly you can go to x7 and reach x8 just like bypass. This is third node. Any other possible ways? Here this way you can jump, but arrow mark is in reverse direction, so it is not. So no other forward paths. So we have only three forward paths. And loops, so this is the first forward path, this is the second forward path, this is the third forward path. Now come to the loops. Loops, this is the first loop, then second loop, then third loop, fourth loop, fifth loop, then sixth loop is a self loop. Of course, self loop is also a loop. Can take this. Then seventh loop is this way and going this way and this way. This is seventh loop. Then eighth loop is from here to here. See, carefully observe, from here to here, then crossing this point x7, then again coming back to x5. So x5, x6, x7, and again back to x5. This is L8, loop 8. Then 9 is this, from here to moving this way and going this way and coming back. See how it is coming back, coming and reaching here, starting it to from x2, going to x7, then again back to, I mean, from here to this way to x2 node. This is ninth loop. Then 10th loop is from here to here it is going, and again it is going this way and coming here like this. This is 10th loop. So this problem is very complicated to find. I mean, number of loops are there. You have to think in all possible ways. Now come to the non-touching. Since there are many loops, we can have a number of non-touching loops, two non-touching loops. So this is L1 now. L1, L2 both are touching only, but L1, L3 are non-touching. L1, L4 non-touching. L1, L5 non-touching. Similar way, I mean, L1, of course, this one also, self loop also, both are non-touching. L1 and L7 also non-touching. Then L1, L6, this is L6 now, L6 also not touching. Then L8 is, L7 is touching, but L8, L1 and L8, this is L8, it is not touching. And L2, this is L2, L4 not touching, L5 not touching. Then L2, L6 also not touching. Then L2, L8, L2 and L8, this is also not touching. Then come to 3. L3, this is L3 and L5 non-touching, L6 non-touching, but L8 is not touching only. So only 2. Then fourth, if you come 4, this is the fourth loop and self loop 6-1, both are non-touching. L7 touching and L8 touching. So remaining all loops are touching. Then leave it. Then L5. L5 L5 L5, this is L5 and L7. L5 and see, this is L7, this is L7 non-touching. Of course, for fourth also L7 is non-touching. So L4 L7 not touching, L5 L7 also non-touching. Remaining all are touching. And then L7, this is L7, L7 and this L8, both are non-touching. So we can, of course, you can also say these are the non-touching loops. Now we will substitute. I think all possible non-touching loops we have covered. 2 non-touching loops. Now come to the 3 non-touching loops. Three non-touching loops. Think 3 non-touching loops. 3 non-touching loops. This L1, L2, L3, L5. Okay, and L1, this, of course, 3 non-touching loops, only one is there, L1, L3 and L5. Remaining all are, only one 3 non-touching loop is there, L1, L3 and L5. You can write it, and after finding this, the procedure you have to find, substitute in the Mason's gain formula by finding delta value and delta 1, delta 2 values, delta 3. Here we have 3 forward paths. So delta 1, delta 2, delta 3 you have to find, and finally substitute in the Mason's gain formula. That is for your practice. You do it. I'm not showing here. You please do it, practice. Now let us go for the one more example. Here block diagram is given. Now we will convert first into the signal flow graph, then we can easily find it, the transfer function. I told you already, each summing point have to keep it as a node, then draw it slowly from C of S. See, R of S to first summing point, there is no gain, that means straight line 1 you have to keep. From C of S to this summing point you have minus H3, because summation is having minus sign, so it is minus H3. Now from E of S to this summing point to X1 node we have G1 gain, and X3 to X1 we have H2 with sign minus. Next X2 to X1 to X2 we have a G2 gain. From C of S to X2 we have connection like minus H1. Then for X3 we have G3 connection and G4 connection to C of S. This is the conversion from block diagram to signal flow graph. Then easily you can find the transfer function. Quickly I will go. Simply you just find the first forward path, then loops, individual loops, non-touching loops, then substitute. Finally, we'll get the transfer function like this. This is a little bit complicated, but it's not a problem. First you convert easily into, signal flow graph. See, this is converted to signal flow graph. Then easily you can find the forward paths, gains, loops, etc. Here, if you closely observe, we have 7 loops. Please identify. This is for your practice. And 3 2 non-touching loops. Therefore, delta and forward path gains, delta 1, delta 2, delta 3. Since we have 4 forward paths here, you please identify all forward paths, then calculate deltas and substitute in the Mason's gain formula. Now let us see one more example. All this for practice, because already explained, we have learned many examples, we have gone through many examples, we already know at this moment the procedure how to calculate. So all this for your practice. Of course, if you see an electrical example, it is also similar to the block diagram. First, we'll write the mathematical equations of a given circuit. Then we will write the signal flow graph or block diagram representation. If you write the block diagram representation, again we have to convert into signal flow graph. Otherwise, you can directly draw the signal flow graph. What is the input and what is the output? We should keep it in mind. Here input is voltage V1 and output is V2. Again voltage. In the middle we have the current. So current in the middle, you can take one extra node. So see the first equation, we have V1 is equal to 1 by Cs I1 of S plus I1 of S into R. So I1 is a node. Easily you can understand here. And that node is connected to V2S in the second equation. So we will write, we have 3 nodes, input node, output node. In the middle we have I1 of S node extra. Now we connect it. How V1 and I1 are related? With the gain of Cs, I mean V1 of S. If you cross multiply it, V1 of S is multiplied with C of S, and also V2 of S is related with, okay, if you write the equation for I of n of S from these 2 equations, we will get Cs into V1 of S minus Cs into V2 of S. So simply from V1 and V2 we got this V1 is a incoming branch and V2 is also incoming branch, but with the negative sign of gains. Gain is same but negative sign. Okay, I1 is related to V1 and V2. We have the expression and we have connected two branches. Then what about since V1 is the input node, it is having all outgoing branches only. So don't bother about it. V2, but V2 should have all the incoming nodes. How V2 is related with I1? Signal should come either from V1 or I1. So here V2 is having a connection from I1 of S and it is having the gain R. So by this we got all the relations connected in the signal flow graph. This is a simple signal flow graph representation of the given network. Whatever, how to calculate the transfer function from the mathematical equations obtained through the KCL and KVLs is a little bit complicated compared to the signal flow graph representation. Here it is very easy. After converting into signal flow graph, can now easily write the forward paths and loops and substitute in the Mason's gain formula. Therefore, you can get easily the transfer function, that is V2 by V1. Take one mechanical system example. Here mechanical translation system is given with the displacements of x1 and x2, and the applied force is given at the first mass. Now before if you want to find the transfer function through signal flow graph, first we have to represent the system in the signal flow graph method, representation. Therefore write the equations. First equation at the first node M1, we have the applied force F is equal to M1 S square, the first opposing force due to mass, M1 S square x1 plus next spring due to spring K1 is contained between mass 1 and mass 2. Therefore K1 into differential displacement x1 minus x2. Similar way, at the second node we have the equation applied force is 0, that is equal to m2, the opposing force at m2 is m2 s square into x2 plus spring opposing force k1, here this spring k1 opposing force k1 into x2 minus x1 plus k2, this spring opposing force k2 into x2. Now from these two equations we can get, after just moving this k1 x2 to this left side, we have this expression. And similar way, if you throw this k1 into x1 to left hand side, we get like this. This is useful for finding the relation between different nodes like applied force x1 and x2. Here in these expressions, or in this model, you can easily say that what are the variables. F is a variable, x1 is a variable, and x2 is a variable. All these are the constants. K2 is a constant, m2 is a constant, k1 is a constant, m1 is a constant. So these three are only the variables. That too, f is the input variable and output variable is the final displacement x2. So intermediate variable is x1. So clearly we can place the nodes in the signal flow graph. We have three nodes, one input f, one output x2, in the middle x1 node. So we need to write first the expression relations to represent the signal flow graph. Relations we need? F1 relation, no need, because it's the input node, all it will give. But x1 relation we need and x2 relation need. That means x1 is equal to something and x2 is equal to something we need. So we'll write from these two equations, x1 is equal to something. From this first equation, x1 is equal to, we can write, so we need three nodes. So if x1 is equal to, from these two we have here also x1, and if you write this total x1 expression in this and simplify it, we will get x1 is equal to, in terms of f and x2, like this. Similar way, if you write x1 x2 relation, if you just throw this to this side, we will get this expression. Okay, here b is nothing but this overall thing we have assumed like b. Okay, and here this m1 square plus f1s plus k1 we have assumed like a. Therefore, if you throw this a to this side, f by a, k1 by a, x2 will come. So 1 by a f plus k1 by a into x2 is equal to x1 we have. Similarly, if you assume all this, the total this term is equal to b, then k1b into x1 is equal to x2. Now we got the relation for x1 and x2 in terms of other variables. Now we'll draw the diagram, signal flow graph, from these two equations. First place the nodes f, x1, x2. Then what is the relation between f and x1? x1 is equal to, because f is equal to, we should not write, because f is the input node. So only x1 is equal to f, what is again 1 by a. So 1 by a, place it. It is the incoming to x1. Similarly, one more incoming is x2. From x2 we have one incoming branch that is having the gain k1 by a. From the second equation, x2 is equal to x1 into something. So only from x1 it is having the signal with the gain k1 by b. Signal flow graph is done. So see, the mechanical translation system, say looking say little bit. Of course, it is not a too complex one. It's a medium kind of translational system. But if you want to try with the block diagram reduction technique, it's a very, I mean, I have to write the mathematical equation, simplify it, and draw in a block diagram way and reduce the block diagrams. Of course, with two masses, maybe not that much difficult, but if you increase the m1, m2, m3, and so on, it will look complex. Therefore, using signal flow graph method is easier. From this obtained signal flow graph, let us find the transfer function. First, find the forward path. This is a straight one line forward path, only one forward path, that is k1 by a into b. And what are the loops? We have only one loop. This is a single loop. Single loop is there. Now delta is equal to 1 minus of loop. So loop is V11, only one loop. And delta 1 is 1 minus. If you remove this first for forward path, there is no loop exists. Therefore 1 minus 0, it is 1 only. Now substitute it here. This is the operand transfer function. This way, for any system, electrical or non-electrical systems, using signal flow graph method, it's very easy to find the transfer function compared to the block diagram reduction technique. In this video, we have learned the Mason's gain formula applied to different examples, and we have learned the solutions, how to find how to convert the block diagram into signal flow graph, and how to derive the transfer function. And we also have seen one electrical, how to get the signal flow graph representation for the given electrical model and mechanical model, and also how to get the transfer function of those models using signal flow graph representation. Thank you.